In this lesson, we learn some clever techniques to count. The most important principle that we will learn is the multiplication principle. Through a series of examples, we will see its effectiveness in tackling a number of different problems. We will also see examples where the blind use of the multiplication principle leads to disaster. A thorough understanding of this principle is important to be able to use it well. Just using it as a formula will never work. Let's begin our introduction with a simple example. You have 4 shirts and 3 pants. In how many different ways can you choose a shirt and a pant? Let's set up some notation. I'll denote the shirts by S1, S2, S3 and S4 and the pants by P1, P2, P3. To pick a shirt and a pant, I could go S2 and P3 or S1 and P1 or S4 and P3 and so on. Now if I randomly pick a shirt and a pant, how am I sure that I have covered all possibilities? How am I sure I have not repeated a possibility that I covered earlier? So I need a systematic way of going about this selection. I need to be sure at the end of my procedure that I have all choices of shirt and pant. Let's try that. I begin by picking shirt 1. Having picked shirt 1, I will pick all possibilities of pants that go with this shirt. Those are P1, P2 and P3. Now I pick shirt 2 and do the same thing. With shirt 2, I can pick P1, P2 or P3. Similarly, with shirt 3, I could pick P1, P2 or P3. And with shirt 4, likewise, I could pick P1, P2 and P3. This looks exhaustive to me. I've picked every possibility of shirt, following which I've picked all the pants that could go with it. It doesn't look like I've repeated anything, and it doesn't look like I've missed out anything. Let's count the number of pairs I have. With shirt 1, I have 3 pairs. With shirt 2, I have 3 pairs. With shirt 3, I have 3 pairs. And with shirt 4, I have 3 pairs. So I totally have 4 into 3 equal to 12 pairs. The shirts and pants were just a useful tool to grasp what was happening. Let's abstract it a bit. We can say that we have a set with 4 elements and another set with 3 elements. The number of ways to pick an element from the first set and an element from the second set is 4 times 3. 4 times 3. That's exactly what happened in the shirt and pant example. What we have just shown is an example of the multiplication principle, which states that if I have a set with m elements and another set with n elements, then the number of ways to pick an element from the first set and follow that up with an element from the second set is m times n. M times n. The important thing to note here is that an element from the first set is being picked and an element from the second set is being picked. Let's see some applications of this principle. You have 7 different mathematics books and 4 different history books. In how many different ways can you pick a book on mathematics or a book on history? Now this is really simple. I have this powerful principle to use, so I'll apply it. The total number of ways is 7 times 4 equal to 28 ways. Hold on. Do you think you're correct? Read the question carefully. It says in how many different ways can you pick a book on mathematics or a book on history? We aren't picking a book of mathematics and following that up by picking a book on history. So the multiplication principle isn't applicable here. What are we trying to do? We're trying to pick one book How many total books do we have? We have 7 plus 4 equal to 11 books. How many books do we want to pick? One book out of these. What are the number of ways you can do it? Well, just 11. So, blindly using the multiplication principle here, just because you saw books on mathematics and books on history, is silly. You have to read the question carefully. So let's look at a slight generalization of the multiplication principle. Sticking to our previous example of shirts and pants, we now add 2 hats into the cover. Then how many different ways can you choose a shirt and a pant and a hat this time? I'll choose shirt 1, follow it up with pant 1, which now can be followed up with hat 1 or hat 2. Similarly, shirt 1 followed with pant 2 followed by hat 1 and hat 2. And shirt 1 followed by pant 3 followed by hat 1 and hat 2. You see what's happening here? I fix a shirt, then I pick a pant, and I fix that pant too, and then pick all choices of hats. In this way, I've exhausted all possibilities of picking shirt 1. I could do that with shirt 2, pant 1, followed up by hat 1 and hat 2, pant 2, followed up by hat 1 and hat 2, and pant 3, followed up by hat 1 and hat 2. Of course, I could do the same for shirt 3 and shirt 4. Now, how do I go about counting this in a systematic manner? So you see, with every shirt fixed, I have to pick a pair of pant and hat. There are 3 pants and 2 hats. So by the multiplication principle, there are 3 times 2 ways of picking pairs of pants and hats. And there are 4 shirts in all. So by the multiplication principle again, there are 4 times 3 times 2 ways of picking a shirt and a pant and a hat, which gives us 24 ways. As you can see, I've listed the ways S1, P1, H1, S1, P1, H2, all the way to S2, P3, H2. I leave it to the student to list the other ways, which would involve all possibilities for shirt 3 and shirt 4. Let's talk about this example a bit more. So, I can pick a shirt in 4 ways. I can follow that up by picking a pant in 3 ways. And I can follow that up by picking a hat in 2 ways. Since every possibility of shirt is paired with every possibility of pant, and then paired with every possibility of hat, the multiplication principle is applicable. And we get 24 ways. The crucial thing here is that every possibility from a given set is paired with every possibility from every other set. We've just seen an example of the generalized multiplication principle, which goes as such. Suppose I have k sets, and the number of elements in each of those sets is n1, n2, up to nk respectively. Then the number of ways to pick an element from each set is n1 times n2 times all the way till nk. Now that we have the power of the multiplication principle with us, let's quickly go over the standard examples that appear in every textbook. Let's first look at coin tosses. A fair coin is tossed. List all the ways it can land. What do we mean by a fair coin? Another word they use for fair is unbiased. It means a coin that does not favor one side over the other. Both sides have an equal chance of appearing when you toss it. Let's denote the two faces the coin can land with H for heads and T for tails. So list all the ways it can land. It can land on a head or on a tails. Two fair coins are tossed. List all the ways they can land in a systematic manner. We follow the example we did earlier regarding shirts and pants. So I'll denote the two coins by coin 1 and coin 2. Now coin 1 could land on a head, following which coin 2 could land on heads or on tails. Coin 2 could have landed on tails, following which coin 2 could have landed on heads or on tails. So there are two ways in which coin 1 lands on a head followed by all the possibilities for coin 2, and there are two ways in which coin 1 lands on a tails followed by all the possibilities for coin 2. So totally there are 2 times 2 equal to 4 ways. It's a simple application of the multiplication principle to see this. Set 1 has two elements, H and T. Set 2 also has two elements, H and T. So the total number of ways you can pick an element from set 1 and an element from set 2 is 2 times 2 equal to 4. Let's move on to tossing 3 coins. List all the ways they can land in a systematic manner. I will of course use the result of the previous example and just copy the number of ways 2 coins can land and tag it on to each choice for the third coin. Coin 1, coin 2, coin 3. Now coin 1 could of course land on a heads, following which coin 2 and 3, I already know the combinations they can land. They are head head, head tail, tail head and tail tail. That exhausts all possibilities that can go with coin 1. Now coin 1 could land on tails, following which we would again get head head, head tail, tail head and tail tail. So totally there were 4 ways in which coin 2 and coin 3 could land, and each of these 4 ways goes with every possibility of coin 1. And by the multiplication principle, I get 2 times 2 times 2 equal to 8 ways. Let's extend this to n coins. I toss n coins. What is the total number of ways they can land? So I have coin 1, coin 2, coin 3, all the way to coin n. Each of them can land in 2 different ways. 2, 2, 2, 2. Is the multiplication principle applicable? Of course it is, because I want to find out the number of ways coin 1 can land, and coin 2 can land, and coin 3 can land, and so on till coin n can land. So the total number of ways is given by 2 times 2 times 2 times all the way till the nth 2, which is equal to 2 raised to n ways. We now have a powerful formula that can allow me to count the number of ways any number of coins can land. So for instance, if I wanted to know the total number of ways 5 coins could land, I would just put n equal to 5 and get 2 raised to 5 equal to 32 ways. To really get a hang of this formula, you should actually list out the 32 ways. The way to do it is to work with the 3 coin example we used, build up to 4 coins and then to 5 coins. Let's move on to another very standard example, that of throwing a number cube or a die. Die, by the way, is the singular form of dice. So I have a 6-sided number cube or a die and I roll it. In how many ways can it land face up? A 6-sided number cube is numbered, has 6 faces numbered 1, 2, 3, 4, 5 and 6. So when I roll it, there are 6 ways in which it can land. The answer is 6. Two unbiased dice are rolled. Use the multiplication principle to calculate the number of ways they can land. So, die 1 and die 2. Die 1 has 6 ways it can land. Die 2 also has 6 ways it can land. Since each choice of die 1 can be paired with each choice of die 2, by the multiplication principle, the total number of ways die 1 and die 2 can land is 6 times 6 equal to 36 ways. Let's look at some of the ways we can get this. So die 1 could land on a 1 followed by die 2 on a 3, or die 1 could land on a 6 followed by die 2 on a 6, or die 1 could land on a 3 followed by die 2 on a 4, and so on. Of course, I need a better way of listing this than this totally random method. And here it is. We have listed all 36 ways in this table. Down the rows we have the numbers for die 1 and across the columns we have the numbers for die 2. So for instance, if die 1 were to land on a 2 and die 2 were to land on a 5, I would get 2, 5. If die 1 were to land on a 4 and die 2 were to land on a 1, I would get 4, 1. Similarly, if die 1 were to land on a 5 and die 2 were also to land on a 5, I would get 5, 5. So you see, all 36 options are listed. It is important to realize that the option 1, 6 and the option 6, 1 are different. 1, 6 means die 1 landed on a 1 and die 2 landed on a 6. 6, 1 means die 1 landed on a 6 and die 2 landed on a 1. Let's stay with the same example. Two unbiased dice are rolled. Find the number of ways they can land so that the first die shows an even number and the second die shows an odd number. Now, of course, the answer isn't all 36 ways, but the multiplication principle still comes in handy. How many ways do we have for the first die to land? So now die 1 has 3 choices, 2, 4 and 6, the 3 even numbers. Die 2 has 3 choices, the 3 odd numbers. Since we want an even number and an odd number, we can use the multiplication principle to get 3 times 3 equal to 9 ways in which the dice can land when the first die lands on an even number and the second die lands on an odd number. Let's mix up the dice and the coins. A fair coin is tossed and an unbiased die is rolled. Find the number of ways the coin lands heads and the die lands on a number greater than 3. So the coin has essentially one choice, heads. The die has choices 4, 5 and 6, the numbers greater than 3. Since every choice of the coin can go with every choice of the die, we have 1 times 3 equal to 3 ways that this coin and this die can land. There are, of course, limitations to the multiplication principle. If you use it blindly, you're going to get caught. Here's an example. 2 unbiased dice are rolled. Find the number of ways the dice can land so that the sum of the numbers on the 2 dice is 7. Let's see some of the ways you can get a 7. Dice 1 could land on a 3 and die 2 could land on a 4. Die 1 could land on a 1 and die 2 could land on a 6. Or die 1 could land on a 6 and die 2 on a 1. But is there a multiplication principle at work here? For the choice of 3, are there many choices of die 2? No, there is only one choice of die 2 that works with 3 for die 1. This is because we are adding two numbers to get 7. So there is no multiplication principle at work here. What we have to do is actually list out all the ways that give 7. Let's do it in a systematic manner so that as usual we know we haven't missed anything. So I start with the smallest number possible in die 1 and build up. So here goes 1, 6, 2, 5, 3, 4, 4, 3, 5, 2 and 6, 1. So I've covered all the ways die 1 can land. 1, 2, 3, 4, 5 and 6. Which each of the ways I've covered all the ways die 2 can land to give a sum of 7. In this case there is only one other way. 1 plus 6, 2 plus 5, 3 plus 4, 4 plus 3, 5 plus 2, 6 plus 1. Counting these ways, we get 6 ways in which we can get a sum of 7. The reason I've spent so much time on this simple example is to emphasize that there is no multiplication principle at work here to help us out. We just had to list each of the ways to get the answer. Okay, so 2 unbiased dice are rolled. Find the number of ways the dice can land so that the sum of the numbers on the 2 dice is less than 5. Again, suppose the first dice is a 2. I could get 2, 1, 2, 2, both of which have sums less than 5. Suppose the first number is a 6. Then I have no ways in which it can go because 6 is already greater than 5. So, depending on which number lands first, the second number is dependent on that. Again, there is no multiplication principle at work here. We actually have to write down all possibilities. I fix a number on the first die and see what all go with it on the second die. So, say a number 1 falls on the first die. What are the pairings with die 2 that work? Surely 1, 1, 2 is less than 5. 1, 2, 3 is less than 5. 1, 3, 4 is less than 5. 1, 4 won't work because 5 is not less than 5. So, if die 1 falls on a 1, we have 3 possibilities of getting a sum less than 5. Let's move on to die 1 landing on a 2. We get 2, 1, 2, 2. 2, 3 onwards won't work because we've reached 5. Similarly, if die 1 lands on a 3, we get 3, 1. 3, 2 onwards won't work because we've already reached our sum of 5. You count these ways, we get 6 ways in which we get a sum less than 5. Again, we had to list all the ways to achieve our count. There was no quick method. Okay, let's stick to the 2 dice rolling example. This time, find the number of ways the dice can land so that the sum of the numbers is even. Again, it's a sum problem. So it looks like I'll have to count all the possible ways I can get a sum of even. Isn't there some other shorter way to get this? Well, in this case, it looks like the properties of numbers might bail you out. When is the sum of 2 numbers even? If both the numbers are even, because even plus even gives even, or if both the numbers are odd, because odd plus odd also gives even. Of course, even plus odd gives odd, and odd plus even gives odd. So these are the only ways I can achieve a sum that is even, either if both numbers are even or if both numbers are odd. Here's where the multiplication principle comes in. I will do both possibilities separately, 1 and 2. So let's count the number of ways 2 dice can fall when both numbers are even. Since there are 3 even numbers, the number of ways both dice can fall with both numbers even is 3 into 3 equal to 9 ways. Now let's count the number of ways 2 dice can land when both numbers are odd. The first number being odd has 3 ways, and the second number being odd also has 3 ways. So we have 9 ways in all. Note that the multiplication principle is applicable because every even number is allowed to be paired with every other even number, since we are adding them to get an even sum. Now what's the total number of ways? We had 9 ways where even plus even gave even, and we have 9 ways where odd plus odd gave even. So the total number of ways is 18 ways. So you see, this question, though it didn't look like a multiplication principle question, could, after a little analysis, be reduced to 2 multiplication principle questions. One where even plus even was counted using the principle, and the other where odd plus odd was counted using the multiplication principle. However, we had to do that initial work to be able to use this principle.